Hey guys, welcome to this new series that I'm starting with AP Chemistry. I'm going to be going over every single unit and subunit that I can, and we'll be covering every single thing so you guys are ready for that exam in May. I remember AP Chemistry being extremely difficult, so I want to make sure that you guys can learn it and we'll both be prepared. So, without ado, I want to start with just a fun joke that I'll be starting with all these videos. You know, it's always good to start off on a positive note. So, it's based on our theme today, which is moles and molar mass. What kind of tests do chemists like best? Well, a multiple choice. Alright guys, let's start this video and let's get into chemistry. Just a reminder, I highly recommend that you guys check out the AP Chemistry Official College Board CED course and exam description, the 2024 version. All the information that I will be talking about in this video is on that. So, without ado, let's get into it. Alright guys, let's talk moles. What is a mole? Well, first, let's remember that moles and molar mass will be super important in calculating future stoichiometric equations. So it's really important that we get this subunit down. Alright, so let's recall Avogadro's number, our friend Avogadro, which is equivalent to 6.02 times 10 to the power of 23. Now, you don't need to memorize this number, thankfully. It will be on your formula sheet that you get for the AP exam. But let's talk about it. Now, what is this number? Well, it's the number of things that you have in a mole. Particles. Things. I know. Such a complex sentence sounds really simple, but let's look at it through an analogy. If you have a dozen eggs, we know that that's equivalent to 12 eggs. Now, a mole is the same idea. 1 mole is 6.02 times 10 to the power 23 particles of that specific molecule of substance. Now, here's where it can get kind of confusing. Even though we have a mole of a substance, that does not mean that the mass of the substance is equal to 6.02 times 10 to the power 23. For example, if we have 1 mole of pure carbon, it's going to have a different mass than 1 mole of glucose, C6H12O6. And it makes sense. Glucose is a much complex molecule, and pure carbon is just an element. Well, let's go back to our dozen egg example. If we got a dozen eggs, each dozen will not weigh the same because every egg is different in mass. Let's say we have a dozen ostrich eggs. Let's say we have a dozen quail eggs. A dozen chicken eggs. They all contain the same number of eggs, 12, but they're all going to be different masses. You know, ostrich eggs are huge in comparison to quail eggs, which are really tiny. And chicken eggs, the ones that we eat, are pretty normal sized. Now, let's look at a real life chemical example. Carbon. If we find the mass of a mole carbon, it's going to be a lot smaller than glucose. Now, a mole of any substance converted into mass is going to be found by using the atomic mass units, or AMUs, that will be found on the periodic table. Now, I highly recommend that you use the AP Classroom periodic table that will be given to you on the AP exam. And we're going to use those atomic mass units to convert into molar mass, which is in grams. Now, here's the nice part about molar mass. Molar mass and AMUs are equivalent. So let's say we want to find the molar mass of a mole of carbon. Now, we're just going to go to the periodic table. And we see that a mole of carbon is 12.01 AMUs. This is the same situation for every element. The AMUs is equivalent to 1 mole of that element. Now, since AMUs and molar mass is equivalent, a mole of carbon is 12.01 grams. Now, let's go back to a more complex molecule, like our glucose. But in this case, let's use a new one. Let's look at caffeine. All right, caffeine. Not really a big coffee drinker, but it's okay. We have 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. Now, there's more steps in finding these molar masses of a mole in these more complex compounds. We're just going to have to multiply the AMUs of each element by the ratio, and then we're going to add them together. So we have 8 carbons. So it's going to be 8 times the atomic mass unit of carbon, which is 12.01, plus 10 hydrogens, and we're going to multiply that by the AMUs of hydrogen, which is 1.01. We're going to add that, do the same thing to nitrogen. 4 nitrogens, AMU of nitrogen is 14.01. 2 oxygens, so 2 times 16. And that gives us 194.22 AMUs. And remember, AMUs and molar masses are equivalent. So 194.22 AMUs equals 194.22 grams over moles, or just grams. But grams over moles is the unit of molar mass. So I'm going to give you guys 3 more examples that I want you to solve. Pause the video and I'll put the answers up after about a couple of seconds. So we have 1 mole of methane, 1 mole of water, and then we have 1 mole of, let's do nitrogen. Alright, so I'm going to give you guys a minute and come back once you finish and solve those. Alright, so I put the answers up for each example, and we're going to move on. So, now that you know how to find the exact mass of an exact mole, let's look at when you have less than a mole. Or what if you want to convert from grams to moles? Or what if you have 5 moles and you want to convert to grams? Now, this is where conversion factors come into play. Conversion factors. Really important vocabulary phrase. Now, this is seen in dimensional analysis. But in this subunit, we're going to be looking at 2 main ones, going from moles to grams and grams to moles. So, when you want to convert moles to grams, you're going to want to have moles in the denominator. So when you multiply the units, they cancel out. So it'll be grams over moles. So it will look like moles times grams over moles. When you are converting grams to moles, it's the opposite. You want grams to be in the denominator. So it will look like this. Grams times moles over grams. Let's look at our caffeine example. Let's convert both ways. First, moles to grams. So let's say instead of 1 exact mole, we have 4.3 moles of caffeine. Well, we already have the mass from the previously calculated molar mass of 1 mole of caffeine. So the dimensional analysis will look like this. We're going to multiply 4.3 moles times the molar mass of caffeine, which is 194.22 grams. Remember, over 1 mole. Now the moles are going to cancel out. Let me just write this out. All right. So now we have 835.1 grams of caffeine in 4.3 moles of caffeine. All right. Now let's say we have 129.45 grams of caffeine. How many moles in that? Well, let's use the other conversion factor. If we have 129.45 grams of caffeine, we're going to multiply by 1 mole over the molar mass of caffeine, which is 194.22 grams. And that comes out to about 0.66651 grams or moles of caffeine. So 129.45 grams of caffeine is 0.66651 moles of caffeine. And I did 5 sig figs because we have 5 sig figs in our initial conversion factors. Now, I know that's a lot of info that we just went into, but this subunit is so crucial for future units and stoichiometric equations, which is just crucial in chemistry overall. Remember your moles and grams. I'll leave you off with 3 fun challenge problems using conversion factors, and I'll put the answers in the descriptions with explanations. So here they are. 2.345 moles of water to grams. 137.3 grams of glucose to moles. And let's do 456.3 grams of NO2 to moles. All right. Have a great day. Happy studying. And I wish you the best. Bye.